This is just a short video on use of the Born-Haber cycle to determine heats of reaction or heats of change in an indirect way. So what I've done is I've already mapped out a change of sodium and chlorine gas from the elements all the way through this path to sodium chloride. And what I've left undefined is what would be the direct change in energy if we just took the elements, sodium and chlorine, mixed them together, and formed sodium chloride. Now we would call that the enthalpy of formation because it's from the elements. We would call that, if we're going that way, the enthalpy of standard heat of formation, or the enthalpy of reaction. When you see that F and you see this, that would be the standard enthalpy of reaction from elements to some product. We call that standard heat of formation. So we can find this in an indirect route by doing this sort of cycle around the top and down. So let's do that. So let's talk about where we are here and go up to this level. Where we are here is we have sodium solid. And to take sodium solid to sodium gas, this is my balloon, we have to add energy. So we know it's going to be a positive delta H. So let's just say it was 10, just 10 kilojoules per mole. But just to show the process, we'd go up 10 kilojoules per mole, 1 mole of sodium solid to 1 mole of sodium gas. And then in this change, we take the sodium gas and the gas of Cl2, and we only change one of these. This just comes up to a higher energy because the Cl bond is broken. So we have half a mole of Cl2, and we break every single bond between the chlorines to make single atomic chlorine atoms. So that would also be energy to break bonds. That would be a positive. So let's just say that's also 10 kilojoules per mole. Now let's watch the next two transitions because that's going to involve electrons. Let's say we could bring a mole of electrons into this chlorine to make from chlorine monatomic form, a mole, to chloride, the anion, a mole of these. Well, we'd need a mole of electrons, and that's I guess that's defined by electron affinity, which for the first electron coming on is always negative because it can attract electrons to the nucleus. So let's say that was a -5 kilojoules per mole. Now we've left unchanged the sodium, so let's now change him with the mole of electrons that had to be given to chlorine. Well, they're coming from the sodium. Let's take a mole away from the sodium, a mole of electrons. Let's take a mole of electrons away from the sodium. Well, that takes energy. That's ionization energy. So let's say that was +5. I know I'm being very simplistic with the numbers, the quantitative part of this, I guess, explanation of the Born-Haber cycle, just so you see how it connects back to the concept. The concept doesn't change, the numbers might. So now we're ready for what's called the enthalpy of lattice formation, or I'll just say LATT. This is the heat or lattice, the enthalpy of lattice formation. To take it from the gases that are not just in the atomic forms but in the ions, and from the disparate corners of the universe, the mole of sodiums come together with the mole of chlorine ions, chloride, and those two ions, a mole of each, come together to make sodium chloride. That's the enthalpy of lattice formation. That's a very, very strongly negative value. Well, we can use, let's say if it was -30, we can use all these numbers that we've just put into the path to find this enthalpy of formation. Follow me on this. What we're going to say is I left this point and I went up 20 in numbers, 10 plus 10. This -5 canceled with this +5, but we would subtract whatever real number we have here and we'd add this number, and I just made it simple so they cancel. And I went down 30, so I went up 20, these canceled, and I went down 30. So I would have, I know for sure, a -10 as a standard heat of formation value in kilojoules per mole. If we were using, again, if we're using mole amounts, we'd find the kilojoule amount. So we can say that's a -10 drop. Now you can play this game any way you want. Let's say that was undefined and I'd known that this was -10. you can start off with this point and roll around up to this point to find the difference between these two. It's a cycle. You can use it any way you want. So let's say you were starting right here. That's you. And you wanted to find out what's the difference in energy between this point and this point. Well, of course, your path would be different now. You're not, I guess, coming this way. You're going up. So you're saying plus 10, plus 10, plus 10. So I'd be going up 30. These cancel out, and we'd be now at this point here. We'd climbed up 30, dropped down 5, plus 5, and now we would have a 30 kilojoules per mole difference between this point and the point that you land on. And you were adding up your numbers as you ought to, adding them when you go up and subtracting them when you go down. Let me say it again. If we started here and we climbed up this cycle, we would add up the numbers. So it's plus 10 because we're going this way, not minus 10, plus 10, plus 10, plus 10, minus 5, and then plus 5. Well, that'd be an increase of 30 kilojoules, and that's what we would have as a difference between this point and this point. And we would report the enthalpy of lattice formation as still minus 30 because we're looking at this difference from top to bottom. Heat of lattice formation is always very negative. Hey, that's it. That's a really short video. I hope that helps with the Born-Haber cycle, how to use it. Again, you can find any of these arrows. Typically, most problems will have you finding this one, using the standard enthalpy of formation, or finding standard heat of formation or enthalpy of formation, knowing this arrow here. Bye-bye.